Thanks, and today I'm going to share some results from our recent work using low-cost sensors for monitoring air quality impacts from smoke events. First, a little bit about the motivation for our project. In the western U.S., wildfire smoke is one of the most significant air quality challenges we are facing. The West experiences frequent large wildfires, and our fire seasons are lengthening and increasing in the acreage burned, meaning that the situation is only getting worse, as illustrated by our current wildfire season. Shown here are widespread smoke impacts from major smoke events in the past few years, including fires in the Pacific Northwest in 2017, the 2018 Camp Fire in Paradise, California, and this year's recent wildfire. As you can see, the impacts of these large events are often regional in nature, causing widespread smoke across the entire western U.S. This slide provides a summary of California's 2020 wildfire season as of September 30th. 2020 is the largest wildfire season recorded in California's history. There have been over 5,000 fires that have burned over 4 million acres in California, nearly 5% of the state. There are 13 wildfires that have burned at least 15,000 acres each, including large fires in Northern California, the Sierras, and the Santa Cruz Mountains, many of them sparked by intense thunderstorms and lightning in August. Since August 15th, there have been 26 fatalities and over 7,000 structures destroyed, and 5 of the 2020 fires are now in the top 6 largest fires in state history. Sadly, we expect these numbers only to increase, and our current wildfire season is ongoing until we do get significant rainfall. This is a smattering of recent media press on the wildfires and how to understand the resulting air quality impacts of these events. Increasingly, the media and the public are turning to sources like PurpleAir sensors to provide air quality information during these types of smoke events, but it's critical for us to understand what the data from these sensors really mean in these settings. Low-cost PM2.5 sensors have widely proliferated in recent years. PurpleAir sensors in particular are widely used by the public and currently comprise the most extensive network of reported sensors, and on the right is a PurpleAir map showing sensor data during the Camp Fire in 2018. These sensors are increasingly used by the public to inform behavioral decisions and risk exposure, and by the media to report on smoke, as you saw in the last slide. But there are gaps in our understanding of how PM2.5 sensors perform during wildfire smoke events. That motivated us to design a project to test sensor performance in smoky environments. We use our regulatory ambient air monitoring network to provide information on the impacts of smoke on air quality, but these monitors aren't cited for smoke impacts and are often sparse, especially in rural areas. It can be challenging to get measurements near all the locations and sensitive populations that we really need, and as a result, we often have large gaps in our air quality information during fires, and it would be great if we were able to supplement these monitors with information from inexpensive sensors that can provide expanded coverage. So we designed our project to deploy sensors in mostly smoky environments alongside reference monitors, allowing us to evaluate sensor performance under both prescribed and wildfire events and across different concentration ranges and ambient conditions. Here's a summary of our experimental methods. We followed several collocation criteria to ensure that the sensors and the reference monitors were seeing the same smoke. We targeted areas where smoke concentrations were expected to be elevated, and as well as opportunistic observations of smoke plumes. And we partnered with multiple agencies to identify measurement locations and get help setting up equipment, and these reference monitors were operated by our partners following their measurement procedures. The sensors were mounted about 1 to 3 meters above the ground and were within 10 meters of the reference monitor and in an open area far away from trees without any obstructions. The measurement sites were at fire stations, Forest Service facilities, and monitoring shelters, and also temporary monitoring locations. We tried to stay away from local sources, but most sites were near roadways, some were unpaved, and there may have been exposure to diesel exhaust sources or smokers, but the prolonged high concentrations of smoke generally minimize the impact of these other local sources. This table shows the 3 sensor packages that we evaluated during the study. All the sensors measured PM2.5, and this was the only reference measurement available at field sites. We evaluated the PurpleAir due to its widespread use, the Aeroqual AQY because it is marketed as a low-cost pollutant monitoring option for our local agencies, and the Sensevere ramp because it was the winner of an interagency challenge for the development of a sensor package for wildfire smoke, the Wildland Fire Sensors winner. We sampled at 4 sites across the country, different fires, different seasons, different concentration ranges, and different reference instruments. The Natchez wildfire in Northern California had prolonged high concentrations and a comparison to a temporary smoke monitor. The Alder wildfire in the Sierra Nevadas had prolonged high concentrations as well and a comparison to a federal equivalent method instrument. And the Pole Creek Mount Baldy wildfires were an example of low smoke concentrations. The Air site on the East Coast is on the EPA campus in North Carolina and was opportunistic sampling for prescribed fire smoke that impacted the area. We measured smoke in all AQI categories, so that's the air quality index, and over a wide variety of ambient conditions as shown in the figures. Most of the fires occurred under dry conditions, so may not have fully captured the full meteorological impacts of measuring smoke, but we did see a wide range of temperature and relative humidity conditions in our long-term monitoring in North Carolina, which is the bar on the far right. These plots show the correlation between sensor and reference PM 2.5 concentrations at several of the locations where we were able to measure smoke. We found that the sensors were generally well correlated with the PM 2.5 from the reference monitors, but typically were biased high in smoky environments, and the sensors varied in performance and showed different biases, indicating that the models we needed different corrections or adjustments to bring them in line with the reference PM 2.5 instruments. Using our data, we then developed correction factors for the different sensors in both smoky conditions and also based on ambient data collected at the EPA site where conditions and concentrations were typically much lower. The figures show the bias for these two corrections for smoke impacted data for each sensor as a function of the reference PM 2.5 concentration. We found that the smoke specific concentration factor or correction factors performed much better than the ambient correction factor, particularly for the AQY on the left. For PurpleAir, although the smoke specific correction factor performed better than the ambient one, and ambient correction may provide reasonable results for smoke impacted data. Because the PurpleAir is so widely used, there were other correction equations we could compare ours to. Many of the corrections were similar to ours and also reduced bias in the measurement, but there was some confusion over which correction factor, that is the CF equals 1 for indoors and CF equals atmospheric for outdoors, that made comparisons with other studies a bit difficult. Not everyone listed which correction factor they used to develop their correction, and there is a bit of a difference between the two. And another issue is that the labeling on the PurpleAir data changed, so it was difficult to determine what channel was used for some of these studies as well. Our initial results were limited to lower smoke concentrations, but this year's fire season has allowed us to evaluate the PurpleAir at much higher concentrations. We found a linear response for the PurpleAir up to 200 micrograms per meter cubed. Laboratory studies have shown that this linearity breaks down at higher concentrations, and the PurpleAir stops responding at about 11,000 micrograms per meter cubed. A polynomial correction, you can see the corrections on the bottom right. A polynomial correction may be better to correct the data at these high levels. The quadratic form fit the California fire data well, and a third order polynomial worked even better. We still need to do more smoke evaluations with different sensors and manufacturers and with more variable conditions, especially at high relative humidity and higher concentrations. EPA has also developed a correction factor for more general ambient conditions for the PurpleAir sensor data. 50 sensors at 39 sites across 16 states were compared to federal equivalent method monitors to develop this correction, which is applicable for the entire U.S. The U.S.-wide correction is displayed on the AirNow Fire and Smoke Map, which is a joint project between EPA and the Forest Service. I'll talk a bit more about in a minute. Our data were also used to validate the U.S.-wide correction during these smoke events. We found that the U.S.-wide correction improves the PurpleAir accuracy, so the concentrations have less than 20% error and report the air quality index category correctly 93% of the time. They also are within one AQI category of the reference 100% of the time, and most of the remaining disagreement is at the AQI category boundaries, unsurprisingly, so right at the lines between these different categories. EPA is using the US-wide correction factor to add a pilot sensor data layer to the AirNow fire and smoke map, which you can see screenshots of on the right. The goal is to provide the public with additional air quality information that they can use to protect their health during wildfires and to improve coverage where monitors don't exist. People want information about their air quality, and we know that they'll turn to any source of information in their area. So we're hoping that the sensor map can address gaps in current AirNow monitoring coverage. Feel free to poke around the site. The link's at the bottom right. You can click on the regulatory monitors, which are circles. The squares are the sensors, and the inset shows some more detailed data for one of those monitors. And if you have any questions, contact us. Although we are not directly involved in the pilot data layer, we do have some ability to raise issues to the team. Finally, I'd just like to acknowledge the many people that contributed to this body of work, especially our colleagues with the U.S. Forest Wildland Fire Air Quality Response Program, the National Park Service, and Bureau of Land Management. So thanks to everybody, and thanks a lot.